Hello everyone, very good evening. Today we are going to start the basic concepts of isomers. Okay, basic concepts of isomers. So first we are going to understand what are isomers is. Okay, what are isomers is. Okay, so I'm just going to write definition first here. Two or more compound, two or more compound having same molecular formula, but different in properties are called as isomers. I think Garima just came in a class. Yes. Okay. Are called as beta isomers. Understood what are isomers is? Two or more compounds having same molecular formula but different properties. That properties may be physical or may be chemical. Okay, physical includes boiling point, melting point, smell, odor, color, state. Okay, these are the physical properties. What are chemical properties? Like reactivity, okay, towards other. Okay, so this is nothing but the definition for isomers. Understood? Simultaneously, you have to write it also because I'm going to erase because I need more space. Should I erase that? Just take a screenshot. Yeah.
Done, sir.
Okay. Okay. So now we are going to understand the types of isomers. So I'm writing here isomer. Isomers. Okay. Isomers are beta main two types. We have main two types of isomers. Okay. Number one, we have structural isomers. Structural isomers, or they are also called as constitutional isomers. Very important, you have to remember the name. Constitutional isomers. Okay, structural isomers or constitutional isomers. Second type we have, again very important, it is stereo isomers. Stereo isomers. Understood? These are the two main types. Now we have to understand what are structural and stereo isomers means.
So stereo is also known as configurational, right?
No, beta. For stereo, we had two types: configurational and conformational.
Okay.
So I'm just going to write here definition for both. See, structural isomers are those isomers, they have same molecular formula but different IUPAC name. Okay, so isomers which have same molecular formula, but different IUPAC name. Names. After isomers, we will cover IUPAC name beta. It is again very important. Okay, we will cover the whole IUPAC name like nomenclature first. Okay, so on chapter we are not going to start that. Okay, only we will understand example if will come. Otherwise, IUPAC nomenclature we will cover separately. Okay.
Yes, sir.
Okay. So this is all about the structural isomers. You have to remember they have different IUPAC name. That's all about the structural isomers, because in isomers we know they have the same molecular formula, but they have different IUPAC name. Okay, now I'm going to write definition for stereoisomers. Okay, so again the first thing is same, isomers which have same molecular formula, same IUPAC name, very important, same IUPAC name, okay, are called as stereoisomers. They are called as, but different properties. So I'm writing here, but have different property.
Has
Different property. Okay, are called as stereoisomers. Understood, everyone?
Yes, sir.
Okay. Now we are going to discuss more about. So this is the first type, the structural, and this is the second type. Okay. So now we are going to discuss about the types of structural isomers. Types. Okay. So for structural isomers, we have main 5 types. Number 1, we have chain isomers. Chain. So how we have to read? Chain structural isomers. Okay, how we have to read? Chain structural isomers. Okay, so what are chain structural isomers? If there is a difference in chain, okay, so I'm writing definition. If, okay, so definition till here, isomers which have same molecular formula but different, okay, IUPAC name, and have difference in main chain of the hydrocarbon, okay, are called as chain isomers. So I'm just writing here difference in main chain, okay. Like example, suppose here we have, this is the butane. Is it? This is butane. Understood? We have already gone through that bond line structure in last class. Everyone? Yeah. So can you write that butane like this? See. Now here we have the main chain of 4 carbon here. But here we have main chain of 3 carbon only, and 1 is in substitution. Is it? So molecular formula is the same, and what is it? It is C4H10. Okay, but they have a difference in their main chain, hence they are chain isomers. Understood what is chain isomers is?
yes, sir.
Now we are going to discuss
The second one would be isopropane.
No, it is isobutane, because we had chain 4. But if IUPAC name, if you want to write, it is 2-methyl propane. The butane, and it is 2-methyl propane. Okay. Yeah. See that methyl group is present on second carbon atom, then it is called as iso. Okay. If you want to take one more example, so I'm taking one more example here. 1, 2, 3, 4, and 5. So it is pentane. It is pentane. If I will write like this,
3 isomers, right? And pentane, isopentane,
yes.
and that
neopentane. This is isopentane. Okay. If we can write like this. Okay. So this is neo. Okay. So what is the difference between iso and neo? So when one methyl group is attached on second carbon atom, so it is called as iso. If 2 methyl group are attached on second carbon atom, okay, if this is the main chain, so this is second number carbon atom, right? So if 2 methyl groups are present on second carbon atom, so then they are called as neo. So these are the 3 possible isomers for pentane. Understood? and the molecular formula is C5H12. Understood, everyone?
Yes, sir.
Yes, sir.
Okay,
Sir,
so this,
iso and neo are the common names, right?
yes, they are common names. So here it is a pentane. Here it is 2-methyl butane. Okay, and here 2,2-dimethyl.
Propane.
Yes. So they have all three different IUPAC names. Hence, they are structural, and it is due to the difference in their chain. So they are chain structural isomers. I hope you understood about chain structural isomers, everyone.
Yes, sir.
Yes, I understood.
Okay. Now we are going to discuss the second type. Okay, I am using black ink for that. Second one. Okay. Second is position. Position structural isomers, or they are also called as, in short, position isomers directly, but it is due to the structure. Okay, so I'm writing a condition. I'm just writing condition, not full definition. Full definition you have to design, because you don't have to write definition and all. Yes, you have to construct on your own. For that you have to understand the concept. Okay, so what are positional isomers? If there is difference in position of okay, for position we are taking substitution, okay, substitution, or multiple bonding, or bond. You can write like carbon carbon double bond or triple bond. Okay, or functional group, or difference in position of functional group, are called as positional or position isomers. Okay, again we have to go through with example. So I'm writing here example. So suppose we have taken here again butane. Okay, on butane here we have beta bromine. Okay, so for bromobutane, so this is bromobutane, so I'm just going to write formula for that, molecular formula. So it is C4H9Br. It is the bromobutane. So this is the bromobutane. But if we will change the position of bromine on second carbon atom, so it may be like this bromine. Okay, so first one is 1-bromobutane. Okay, for first position you need not have to mention their position. So instead you can write bromobutane will also do. But here the position of bromine is second, so here you have to mention 2-bromobutane. Understood? The position of substitution is different, so they are positional isomers.
Sir,
Understood,
in
beta?
positional isomers, the IUPAC name is also different, right?
Yes. So here we already gone through in structural isomers difference in IUPAC name. So it will be difference all the time.
Yeah. Yeah.
Yeah.
Okay.
Yeah. That's why we have different name: 1-bromobutane and 2-bromobutane. Okay. Second thing, we can change the position. For next example, I'm taking. Okay. What is it? Butene. But2-ene means it is nothing but CH3 CH double bond CH and CH3. So here position of double bond is between second and third carbon atom, right? Here, but we can think that position of double bond may be on first carbon atom, like this over here. 4 carbon chain, and the position is on here first carbon, right? Is it like this? CH2
Yeah,
double bond CH, CH2 CH3. So here we have the position of double bond is different. So it is again positional isomers. So we are going to write name. So again here we have 4 carbons. So for 4 carbon we are using but. and position of double bond start from second carbon atom. So we have to write 2, and for double bond we are writing ENA. So but 2-in is the name for first one. For second one, it is butene only, because double bond start from first carbon. So there is no need to write the position for first position. Okay, so I'm just writing but ENA. So it is butene. Okay, so this is these two different name. It is due to the difference in position of double bond here. So this is for first example is for substitution, second is for multiple bonding, and now we are going to understand for functional group. Okay, so I'm taking here 3 carbon chain, and on first carbon we have OH group. So it is propanol. Prop is for 3 carbon. No. We have 4 carbon here. So it is butane. Wait, let me check only 3. Okay. So see, here we have one first carbon, second carbon, and third carbon. And just do consider we have OH group. OH means alcohol group on first carbon atom. We're getting the point, everyone?
Yes, sir.
Yes, we're getting it.
It can be written as CH3, CH2, CH2OH like this. So it is propanol. Okay, but we can think position of OH group on second carbon also over here. So it will be like this. Here we have OH group. Okay, so it can be written as CH3, CH, here CH3, and here OH group. So it is propane 2-ol. Propane-2-ol. So this is propane 2-ol. So this is the difference in position of functional group. So on that basis, we have 3 examples. One is for substitution, difference in position of substitution, difference in position of multiple bond, and here difference in position of functional group. So these are nothing but the functional isomers. Understood, everyone?
Yes, sir.
Okay, so for example, just take a screenshot for that.
So for that functional isomers, are there any specific groups which follow this type of isomerism?
For functional isomers, molecular formula will be the same, but different functional group are there. I'll make you understand after that, don't worry.
Yeah, I understood. But are there any specific groups of functions like
Yes. Like alcohol and ether we have. Okay, we'll understand that, don't worry. Yeah. For aldehyde and ketone we have. Okay, done, beta. First take a screenshot from here. Just take a first screenshot from here.
Your voice is breaking actually.
Okay. Okay, so now we are going to discuss about functional isomers. Very important. Okay, see, functional isomers means what? Again, compound, okay, 2 or more compound having same molecular formula but difference in functional group. Difference in functional group. So I'm writing here isomers which have same molecular formula. I'm only writing MF, molecular formula. Okay, different IUPAC name. Okay, and or instead of that you can write and difference in functional group. For functional group I am writing FG. Okay, functional group. Am I clear, everyone?
Yes, sir.
Okay, so first pair we are going to understand. So I am writing here see alcohol and ether. Okay, they shows functional isomerism between them. So this is the pair, alcohol and ether. So I'm just taking ethanol. Ethanol is formula we have C2H5OH is the formula. Okay, or instead you can write also it is C2H6O. You can write like this also. Is it?
Yes,
Okay.
sir.
So now I'm going to write alcoholic group and ether group by using this molecular formula. Okay. So can we write CH3 CH2OH? So this is ethanol. Ethanol. Okay. But can we write like this? CH3 C, oh no, O, and here CH3. It is methoxymethane, or it is dimethyl ether. It is dimethyl ether, or it is also called as methoxymethane. Methoxymethane. Okay, everyone. So here we have, say, molecular formula is the same, okay, but we have different functional group in each pair, each group. Okay, here we have alcoholic group and here we have ether group. So this is the functional isomers. Okay, next example. Second example we are going to have here for aldehyde and ketone. Okay, aldehyde and ketone. Again, I'm taking it is CH3 C double bond OH. C double bond OH. It is beta ethanol or acetaldehyde. So I'm writing molecular formula for that. C2, we have 2 carbon, we have 4 hydrogen, so C2H4 and 1 oxygen like this. C2H4O is aldehyde. Okay, so can we write that CH? No. In order to have ketone, we have to have 3 carbon. So I'm just taking chain of 3 carbon, madam, not for 2.
Yeah, sir. At
CH,
least 3
yes,
carbons are required for ketone.
yes. CH2C double bond OH. Okay, so it is propanol now. It is propanol. So I'm just going to write molecular formula. We have 3 carbon, so I'm writing 3 C3. Then H, we have 3, 2, 5, and 1, 6. So H6 and 1 oxygen. So it is C. Number of carbon we have 3. So for 3 we have prop. All the carbon single bond. So for that we are writing ANE, but instead of E we are writing ul here. Ul. So it is propanol, or it is also called as propanaldehyde. It is also called as propanaldehyde. Okay. So for next, because for ketone we have to have at least 3 carbon atom. For aldehyde we can have single carbon atom also. Okay, but for ketone we have to have 3 carbon atom, because on center carbon atom we have oxygen with double bond carbon. It is also called as carbonyl carbon, and in both the side we have CH3 group like this. Okay, see, we have 3 carbon, we have 3 carbon, we have 6 hydrogen, we have 6 hydrogen, and 1 oxygen, we have 1 oxygen. So molecular formula is the same for both. Okay, but it is also, see, that one is called as number of carbon we have 3, so it is prop. Again, single we have carbon bond, so N, and 2 on. Okay, on is for ketone group. Okay, so here we have aldehyde group and here we have ketone group. See, molecular formula is the same beta, but we have 2 different compounds with 2 different functional groups here for the same molecular formula. So they are again functional isomers. Understood, everyone?
Yes, sir.
Okay,
Yes,
again,
sir.
take a screenshot.
Done, sir.
Okay, everyone done?
Done, sir.
Yes, sir.
Yes, sir.
Okay. Okay, so again, third group, third pair, very important. What is the third pair, Samarth?
Third pair. Wait a minute, let me remember. Was it that? Yeah, carboxylic acid and ether.
Not ether, ester.
Yes, ester. Sorry. Yeah.
Ester. Okay. See, I'm taking example for carboxylic acid. So here, if we will have 2 carbon chain, will do also. So I'm just taking CH3, C, double bond O, OH. It is beta ethanoic acid. It is ethanoic acid. No, we had to have one more carbon. Wait. So I'm taking propanoic acid. So it is CH3, CH2, C, double bond O, OH. Okay, it is propanoic acid. Prop and oic acid. So it is carboxylic acid group. Okay, that functional group is called as beta carboxylic acid. Okay, so I'm just going to write molecular formula for that. So we have 3 carbon, so C3. Total hydrogen we have 3 plus 2, 5 and 1, 6. So I'm writing here H6 and 2 oxygen, so O2. So this is the molecular formula for propanoic acid. So now I'm going to design ester group for that. So for ester group we have CH3C double bond O, CH3.
Sir, we can put the O before also, right?
Which one here?
In the place where you put C double bond O, first we can put O, then C double bond O. Like
No, this is also
it will
correct.
just be the same, sir.
That one.
Yeah.
This is not the
Where
same. This
in
is
the ester, sir.
alkoxy group. Okay, yeah,
Yeah.
we can do that also. This
Yeah,
is a alkoxy group, and this is the like alkanoate group, alkoxy and alkanoate. Okay, so
Yeah.
I'm just going to write name for that. So we have to write name for that first. So it is methoxy. Meth for 1 carbon atom, and it is with oxygen, so it is methoxy. Okay, and here we have 2 carbons, so for that eth, and single carbon, for that we are adding N, and for that particular group C double bond O is called as O8 group. O8. Okay. Yes, so instead of E we are writing OATE. So it is methoxy ethanoate. Methoxy ethanoate. So it is called as ester group. Okay, it is called as ester group. So see here again we have same molecular formula by which we had 2 different compound with different functional group. Everyone understood that? So this
Yes.
is
Yes,
all
sir.
about the functional isomers. Okay, so again I want just take a screenshot one by one. Okay, so now we are going to understand about the metamer. So for metamer, this concept came from the that functional isomers only, from functional isomers. So for that we have to take example of that one, ester. So I'm taking ester. So first we have to understand example, and after that we are going to write definition for that. Will do, or we can take that ether one also. So I'm just taking do you know what is it? Here we have CH3, then we have CH2, then we have O.
Sir, is it ethoxy ethanoate?
Yes. Then CH2 and CH3. So here we have, see, here we have functional group called ether, and both the side we have same alkyl group. Is it everyone? Means both the side we have same number of carbon atom. So it is ethoxyethane.
Yes,
Ethoxyethane. Okay, but again I'm just going to write molecular formula for that. So it is C4H10O. C4H10O. Okay, so it is ether. But if we can think another ether here, like CH3, CH2, CH2O, and CH3. It is also the ether, and only the difference is the chain of carbon atom. Okay, both the side of the functional group. So it is what now? It is methoxypropane. So methoxypropane.
So your voice is breaking.
Oxyproof. Actually, your voice is lagging a bit.
Okay, wait. Okay, and now?
Sir, it just lags for 1 or 2 seconds and then gets clear.
Okay. Again, it is due to the rainy season here. Okay, now understood what is the basic difference between these two? Functional group is same beta. Only the side chain, okay? Another side of the functional group that carbon chain have, there is the difference only, nothing more than that. Okay, so such relationship is called as metamerism or metamers. Okay, so this type of isomer which are arising due to difference in alkyl group which are attached on the same functional group. Okay, so I'm just going to write definition for that. So metamers are the isomers which arises due to difference in alkyl group or carbon chain. Alkyl group attached on either side of functional group. Okay, are called as metamers. Understood, everyone?
Yes.
Okay, so again take a screenshot for metamer.
Done, sir.
Okay. Okay, so this is all about the metamer. So last but not the least, we have fifth one, tautomer. Okay, we will understand that metamer with the help of one more example. Okay, we have just gone through with one example, so we understand with the help of one more example. I'm just taking again that alkoxy alkanoate ether ester group, ester. Okay, so I'm taking CH3, CH2, C double bond O, O, CH3. Okay, so it is methoxypropanoate. It is methoxypropanoate. Can we write that methoxypropanoate?
Yes, sir, we can write that.
Okay. Now here I'm just going to increase the number of carbon atom. Means from one here I'm taking over here. So can we write that like CH3, C double bond O, O, CH2, CH3. Can we write that?
So you are trying to make it ethoxy ethanoate.
Yes. Now it is ethoxyethanoate. Ethanoate. So what is the difference here? That side chain of alkyl group is different in both of the cases. Otherwise, they have the same molecular formula. So I'm just going to write molecular formula for this. Okay. So here we have 4 carbon. So C4. Hydrogen we have 3 to 5, 6, 7, 8. So C4H8 and Oxygen we had 2. So C4H8O2. Understood?
Yes, sir.
Everyone?
Yes, sir.
Okay. Again, take a screenshot for that.
Written in copies.
Okay, everyone.
Yes, sir.
Yes.
Okay. Okay, so now we are going to discuss about the last part, and which is nothing but the tautomers. Fifth one. Any idea about tautomers? Any idea about tautomers? Yes.
Yes, sir. These are a variety of isomers which are nearly equal to the functional group isomers, and they can be classified as what can you say, the cis
Okay.
trans is there. Yeah, that type.
No, not cis trans type. Okay. It is aldol. If you are taking aldehyde and ketone group, so it is aldol type.
Sir, your
Okay.
voice is breaking.
Voice is breaking still. Wait, wait. Okay. So now we are going to understand about tautomers. See, tautomers are again the important concept, but it is really very easy one. Just you have to go through one example here. Suppose here we have beta aldehyde. Okay. So I'm just taking CH3, CH2, C double bond OH. It is the aldehyde one. It is aldehyde. Okay. Suppose I am just going to dissolve, okay, that aldehyde in any organic solution, okay, any organic solvent. Okay, understood that? This
Yes.
is what
Yes,
is the
sir.
name? It is propanol. Its name is propanol. It is propanol. I'm just going to dissolve that solution, that aldehyde or propanol, into any organic solvent. So it is going to dissolve and will change, the position of functional group here. So I'm just writing here, it is CH3, C double bond O, CH3. Okay, it is again in a solution only. It is again in a solution only. But what is the name for that? Again, it is ketone group. Here we have aldehyde group, and here we have ketone group. So I'm writing here aldehyde, and it is ketone. Okay, so for name I'm writing, for ketone I'm writing the name, it is prop, then N and 2 on, propane 2 on is name for that. Okay, so see here, after some time, okay, when we will dissolve that aldehyde into the solution, will acquire equilibrium between these two functional group or these two compounds. After some time it will acquire the equilibrium here, equilibrium. Okay, so that form is called as aldol form, and that form is called as ketol. Okay, ketol. So there is an equilibrium between that aldehyde and ketone group, okay, in a particular solution. That state is called as tautomer, and the property is called as, and that phenomenon is called as tautomerism. Okay, so this is all about the tautomers. Understood?
Yes,
So
sir.
okay, so I'm going to write definition for that. Okay. Okay. So tautomers are nothing but again the isomers. Tautomers. They are the constitutional or structural isomers. Tautomers are the isomers of two compounds. Which are two compounds? Ketone and aldehyde. Okay. Compound means ketone and aldehyde. Two compound means here we have taken, we can take that alcohol and ether also, or we can take aldehyde and ester also, carboxylic acid and ester also. Okay, two compounds that that interconvert form of each other, that or these are or which are interconvert converter, okay, of each other, are called as tautomers. Understood?
Yeah, sir. 1 degree, 2 degree, and 3 degree amines are they tautomers?
1 degree primary, secondary, and tertiary. Yes, they can be.
Yeah.
Even generally, yes, generally that will come again in phenol in 10th class, 12th class. One chapter we have alcohol, phenol, and ether. There we will have again the tautomer, the same thing. Okay.
Okay, sir.
So this is
Sir,
all
it is
about.
also known as the keto-enol constant, right?
Yes. It is
Concentration.
also ketoenol. Okay, just take a screenshot. Done, everyone?
Yes, sir.
Yes, sir.
Okay, so this is all about the structural isomers. So now we are going to discuss about stereo isomers. So for that, I am just moving the screen in this side. Okay, and it is very important. We are just going to understand. It is really very important as your exam point of view, because most of the questions are being asked from stereo isomers only. Most of the time. Okay, so I'm writing here stereo isomers. Again, they are of two types. Number one, we have configurational stereoisomers. Okay, and second we have conformational. Stereoisomers. So these are the main two types of stereoisomers. Samarth, Sadar.
Yes, sir.
Okay. Now we are going to understand the types. Okay. See, configurational isomers are those isomers. Okay. They can be isolated at a room temperature in laboratory. Okay. Configurational isomers or those isomers, they can be isolated at a room temperature in laboratory, are called as configurational isomers. So I'm going to
Okay, sir.
write.
So they are stable at the room temperature.
They can be isolated, yes, but
Yeah.
that conformational, they
Some
cannot be like isolated at a room temperature in laboratory.
They need special conditions.
Yeah. Only special condition like standard temperature and pressure have to be applied there.
Okay.
Yeah. So configurational isomers means those isomers which can be isomers which are stereoisomers. Stereoisomers which can be isolated at a room temperature. Okay, are called as configurational isomers. Now we have conformational isomers. They cannot be isolated at a room temperature. That's all. Isomers which cannot be isolated at a room temperature. okay, are called as configurational isomers. Okay. It is due to what? Suppose if we are taking example of ethane. Okay, so here we have ethane, H, H, H. Here we have H, H and H. So why they are conformational? Because if suppose if we will think about the rotation along with carbon-carbon single bond, so that hydrogen is going to down, okay, and that again going to up. So the compound is not going to change and its properties are also not going to change if there is a change in position of hydrogen. Okay, why? Because here rotation is takes place along with the carbon-carbon single bond. Okay, so I'm just going to write definition. The condition for conformational isomers, they are arises, okay, which arises due to rotation, along with carbon-carbon single bond. Okay, carbon-carbon single bond, C single bond. Okay, that's all. This is all about the conformational isomers. Okay, now we have detail about the configurational isomers, very important. Okay, so configurational isomers again have two types. They are also of two types. Number one, we have geometrical isomers. Geometrical configurational stereoisomers, and second, optical. So optical configurational stereoisomers. Understood?
Yes.
Yeah. So geometrical isomers already we have gone through in last class, but just I'm giving you like small introduction about it. Suppose if we are thinking about carbon-carbon double bond here, okay, and one side we have methyl group and one side we have hydrogen. Here we have one side methyl group CH3 and here we have hydrogen. Okay, so we can see here this same group of element or same atom are present on the same plane. So they are cis. They are cis form. Molecular formula is the same. IUPAC name will be same. Only the position of same element or same group of element on opposite plane. That's all. So this is all about the cis. If we can think differently, suppose here we have again carbon-carbon double bond. Here we have methyl group. Here we have hydrogen. Here we have hydrogen and here we have methyl group CH3 like this. Okay, if we are just checking both the compound, here position of same group, same element or same group of element on opposite plane, right? So if they are in opposite plane, they are called as trans form. Okay, so this is trans isomers and this is the cis one. Understood? This is all about the geometrical isomers. But how these two different compounds are arises? It is due to restriction in rotation along with the carbon-carbon double bond, because rotation is not possible between carbon-carbon double bond. Suppose if you are taking two sticks in your hand and if you want to like keep one constant and rotate other, okay, just keep this one constant and rotate that side. Are you able to rotate that two stick being position over here constant? No, na?
No, sir, it cannot be
Okay,
rotated.
yes. So geometrical isomers, they are arises means we have these two different types. Okay. Hence, these isomers are arises due to restriction in rotation along with carbon-carbon double bond. So I'm writing here isomers. Which isomers? Geometrical configurational stereoisomers arises due to restriction in rotation. Restriction in rotation along with carbon-carbon double bond. Okay, so on that basis, we had two type of isomers. One is called cis and other is trans. What is cis? If same atom or group of atom present on the same plane are called as cis isomers, and if same group or same group of atoms are present on different plane are called as trans isomers. Understood everyone? Cis and trans.
Yes, sir.
Okay. Now we are going to discuss quick about that optical isomers over here. Okay, see, optical isomers means what? It is due to the chiral carbon atom beta. Chiral carbon. What is chiral carbon? See, if all the four valencies of carbon atom are get fulfilled by four different atom or group of atom are called as chiral carbon. Okay, and it is represented by star, steric form. Okay, so we discussed about last class. Okay, if so there arises, so this chiral carbon compound have capacity to rotate the plane of plane polarized light. Okay, they have capacity to rotate the plane of plane polarized light into clockwise direction or in anti-clockwise direction. Okay, such compounds are called as optical active compound. If they rotate in clockwise direction, then they are called as dextrorotatory. And if they rotate in anti-clockwise direction,
It's LIBO.
then they are called as in LIBO group. Okay, so dextro and LIBO, two types of isomers we have. So it is due to the difference in behavior of compound towards the plane polarized light. Okay, how there arises these optical isomers? I'm writing here isomers.
Sir,
Which,
I have a doubt. After you teach this topic, I will ask.
okay, which arises due to difference in wait a second, let me attach the charger because battery is getting down. Wait, otherwise it is going to switch off. Wait. Okay, so isomers which arises due to difference in behavior, of compound towards plane polarized light, PPL. We discussed in last class also ki how like PPL is being produced.
Yeah, Nicholas prism
Yes.
is used to
So
get PPL.
yes, Nicole prism. So number one, we have dextrorotatory. Okay, dextrorotatory, which rotates the plane of plane polarized light into clockwise direction. If they rotate the plane of plane polarized light into clockwise direction, are called as dextrorotatory. And if they rotate like plane of plane polarized light into anti-clockwise direction.
The anti-clockwise direction.
Yeah. Anti-clockwise direction.
I will call as LIBO.
Are called as LIBO, yes. LIBO, L-E-V-O. LIBO. Rotatory optical isomers. Okay, so this is all about the dextro and the LIBO. So wait a second. Again.
Sir, I have a doubt. Sir,
yes.
is the RS configuration same as dextro and LIBO?
Rectus and sinister. It depends. No,
Yes,
beta. Yes, it is due to, but we had to like provide that priority to the all the four valencies which are attached on that chiral carbon atom.
Yes, sir. We have to check that also.
Yes, we have to check their molecular mass. If the molecular mass will be higher, okay, so we have to give priority must first. If it is the lowest one, so it is the last one. So we can select any three carbon atom, three group around the chiral carbon, and we can like give them priority. So on that basis, we can decide that dextro and LIBO also. So that we will cover again the rectus and sinister form RNS configuration. Yeah. Okay. So just have you took screenshot, everyone?
Yes, sir. Written
Yes,
in
sir.
copy.
Okay, so any doubt in that part? Because today we have completed isomers.